today's class, I want to say two things. Okay, one, I am not going to accept any late homework unless you tell me in advance why you cannot submit. And second, I am going to stop, the health class because if students they don't show up to the lecture class, but they show up on the help session, just only to get help how to solve the problems of the homework assignment, then that I'm not going to do. So what I'm going to do is you can come during office hour and ask me any questions that you have with the problem. Sorry, I have to do that. All right, so last time we discussed we began discussing about Maxwell's equation, and all right, so Maxwell's equations. Equations. So in free space, we said that from Gauss's law, the divergence of the electric field is equals to rho over epsilon naught. That is Gauss's law. And the divergence of the magnetic field is that's always 0, and this is M. And the other one is the Faraday's law. The curl of the electric field is equals to what? The change in magnetic field with respect to time. So that is Faraday's law. And the last one is Ampere's, you can call it Ampere's-Maxwell's equation. It says the curl of the magnetic field B minus mu naught epsilon naught change in electric field with respect to time is equals to mu naught times J free. So that is, let's call it Ampere's law. But Ampere's law is without this term, and this term was introduced by Maxwell. So these are the Maxwell's equation in free space. What is going to be the form of these equations in matter? So in matter, so if the medium is polarizable, magnetizable, we saw there are additional currents which is related to the orbital motion and spin motion of the electrons, and that would give you what we call the bound current. So in matter, we have bound currents, JB, which is related to the magnetization current of M. And also, if the material is polarizable, we have polarization density rho bound, which is equals to minus the divergence of the polarization P. But in addition to the bound current density, so this is the bound current density, that is the result of the spin motion and the orbital motion. So this is the result of spin and orbital motion of charge, basically the electron. But if the polarization of the medium is a function of time, these electrons around the nucleus could experience a force which forces them to displace along the radial direction. So when we say spin and orbital, that's due to angular motion, but the charges can move along the radial direction because of polarization, if the polarization changes with time. So that produces another current which is known as the polarization current. So because when a P changes with time, we have a polarization current. Current JP. And this current is related to the polarization. JP is going to be negative of, not negative, just the time derivative of the polarization P. So now, then in matter, when we talk about Maxwell's, for example, Gauss's law, the charge should include, not only the free charge, but also the bound charge density. And when we talk about current, we should talk about, in addition to the free current, we should talk about the bound current and also the polarization current. So if we change the free current to a bound free current plus bound current plus polarization current, then we would have the following equation. So in matter, then Maxwell's equation becomes the divergence of E becomes rho free plus rho bound over epsilon naught. And the other Maxwell's equation that would change is this one. Those equations that explicitly depend on the charge density and the current density are the one that would change.